Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for about 20 years now, and I like to bring you behind the scenes and show you some of the actual astronomers, astronauts, people who are doing the work. And this is going to be another one of those interviews. So today I'm joined by Dr. Thayne Currie. Thayne, welcome to the show.
It's great to be here.
So who are you? What do you do?
All right. As you said, I'm Thayne Currie. Sort of wear two hats. So, I have an affiliate position at the Subaru Telescope as an astronomer, and I also am affiliated with the NASA-Ames Research Center as a contractor through Eureka Scientific. I want to find the next Earth, and I want to understand the context in which the solar system was born. And so, my focus is trying to directly image those, answers to those questions. So, studying planet formation and directly image the planets themselves.
And you actually reach out to me on Twitter, which is very rare. I wish more astronomers would actually do this. And I guess, we followed each other for a little while, but you're like, we've got some big news coming out on Monday. Are you interested in talking with someone? And so we covered it on Universe Today, but then we booked an actual interview because this is a topic that I'm really, really fascinated about. So first, let's talk about the news, and then we'll talk about the part that I'm really fascinated about. So what have you discovered, uncovered, observed?
Well, we end up getting a conclusion that we did not expect when I started on this journey about 5 years ago. So we think that we found evidence for a wide separation protoplanet. So that's a planet in the process of forming, still in the process of assembly, or is still embedded in its natal gas and dust. We think that we found evidence for it at a sort of a wide separation. So about 3 times the separation between the Sun and Neptune around this very well-known star called AB Auriga. So this, if you talk to people in the planet formation community, AB Auriga is one of those things that a lot of people know by name. It sort of rings a bell. And so we think we find evidence for this protoplanet embedded in the disk around AB Auriga. And it seems like this, if we look at other characteristics of the system, this may be best explained by an alternate theory scenario, which is the canonical core accretion model.
And so when we think about how, say, Jupiter and Saturn and other giant planets form, what is this traditional theory?
Sure. So the traditional theory sort of starts from the ground up. So you have very sort of micron-sized dust grains that stick together into slightly larger ones, into pebble-sized objects, and then eventually to boulder-sized objects. And then for the things like the Earth or Mars or Venus, they grow to being, maybe have cores the size of the Moon, and they collide together, and they eventually become, the terrestrial planets.
Right.
So for things like Jupiter and Saturn, we think those cores grow large enough that they start to accrete the gaseous envelope from the protoplanetary disk around them. So the typical sort of the trigger for that, on the order of a few times the mass of the Earth. Like it depends on which theorist you talk to. All right. So that's the sort of canonical model for the accretion of gas around these cores. So this is the core accretion model.
Right.
And so it does a good job of explaining the characteristics of the mass of planets in our own solar system. And a lot of sort of the demographics of planets we've identified through surveys, through both indirect methods and also through direct imaging. But it struggles at very wide separations. Many times the separation of things in our own solar system. Now, we found planets at those separations through direct imaging. We found a few of them. So the question is, how did they form? And we think that this discovery provides a partial answer to that question. Namely, they formed it through an entirely different mechanism.
I'll bite. What's that mechanism?
So the mechanism is disk or gravitational instability. And so this idea has been around for a very long time, actually. I think, even as far as I can remember, I think it was even debated back in the 50s or 60s or 70s. Maybe early researchers like Safronov and Weatherall probably debated it when they were advocating their own models for early core accretion simulations. So it's disk instability is a sort of this top-down mechanism where the disk actually becomes gravitationally unstable and regions of it start to fragment and collapse into clumps. It was revived in the 1990s by Alan Boss at the Carnegie Institution. And he's been sort of like the chief torchbearer for this model. To put it lightly, he's very well known as an advocate of this theory.
Very excited that you found this evidence.
Oh,
sure.
he like it was so like I sent him an email. I forget when it was, like in 2020 or 2021. It's like, hey, Alan, we have a result you'll be really interested in, and I just kind of left it at that. So because we're like left him hanging for at least a year, and then I finally sent him the paper in March, and he was quite happy.
And so what's going on then?
So with the disk instability, with the disk instability formation mechanism, so you have the regions fragment into clumps, and so you have gas giant planet formation from the top down that can happen at very wide separations very rapidly. Right. So the weakness with core accretion is that it takes a long time to kind of get to the point where you can form something several times the mass of the Earth to be able to create gas around it. And in order for it to have a gas giant planet formed by core accretion, not only does it have to happen, does the core have to form before the nebular gas dissipates, but you have to have enough gas left over in the first place to be able to have something the mass of Jupiter or Saturn, or even more massive, form from that. That's very tough to do at 90 AU, which is close to the separation in which we find this protoplanet.
Right, that's like double the distance to Pluto. Like that's really far away.
Double distance to Pluto.
Yeah. And so I guess I'm envisioning, with the traditional sense, you've got like a bunch of little pebbles that accrete larger and larger objects, smash into each other, planetoids. Eventually, they scoop up the surrounding gas, and you've got a planet made of whatever is the raw materials in that area. But what you're describing is like more like the way the star itself forms out of a solar nebula, that some blob of material is far away from the star, and through its mutual gravity collapses down into a planet of its own, and whatever raw material you had in that area to work with. But it's not like the material is being parceled out to different planetary orbits. Everything is ending up in this one planet that's out there.
I think that's fairly similar to how I would describe it. I mean, if you look at the models for planet formation by disk instability, they end up showing like these very pronounced spiral arms or spiral density waves in the disk. It actually makes the whole entire planetary system look almost like a galaxy. This is really cool.
Yeah.
And this is what we see with AB Auriga. There are multiple spiral arms in the disk around AB Auriga on hundreds of AU scale. So this is a huge system, and so I think in sort of way, if there is one very well known planetary system with a disk around it that might be a good candidate for planet formation by disk instability, AB Auriga would be near the top of the list. It's just until now we hadn't actually found the smoking gun for something that might be that protoplanet that is just formed.
So what was the technique and series of instruments that were required to gather this data?
Sure. So the primary one that we used was on the Subaru Telescope. So this is called the Subaru Chronographic Extreme Adaptive Optics Project, or SCEXIO in shorthand. So this is an extreme adaptive optics system. So different than most facility AO systems. So you can kind of sort of think of that as the what you get as with the observatory is sort of like a general use instrument. Extreme AO is different in that the system typically corrects for atmospheric turbulence faster, and with a deformable mirror that has a higher density of actuators across the telescope pupil. Basically, that means that you can correct for atmospheric turbulence faster and with greater precision. So we use that adaptive optics system to be able to get really sharp images of AB Auriga starting in about 2016. And when we fed that sharpened starlight to a science camera, and the first one we used was this now decommissioned camera called Haichao, and then the integral field spectrograph called Keras, which allows us to get images in 22 different channels at the same time, going from about 1 microns to about 2.5 microns.
Right, and so that's firmly in the infrared.
That is firmly in the infrared, yes. So that sort of like forms the backbone of this study. I mean, the choice to actually image the system in the first place was kind of an afterthought. It was kind of an accident. When we went to the telescope on our first data set where we actually got a detection, we were trying to observe something else, actually. So it's actually the system now with refuted protoplanets. So look, calcium-15. So it's a different system. But that's a really faint star, and for whatever reason, we had trouble getting a good correction on that star. So we think, okay, well, our data is going to be useless unless we try to observe something else. And just AB Auriga was the first thing that popped into my head.
Yeah,
these things happen, right? And we get this detection of this blob, and it's kind of peculiar. I was like, oh no, it's probably a processing artifact. All these are, nature hates us. So then we get another detection. It's like, well, it's a really persistent blob. And we just kind of get this gradual accumulation of evidence that starts to change our thinking as to what exactly we were seeing.
and you've been observing this now for enough years that this blob is moving, right?
So if we just look at the Subaru data itself, there does seem to be evidence for orbital motion. The position and angle of this blob does seem to be changed. So it does seem to be moving counterclockwise. But the real proof would be is that if we observe it on a longer time scale, right? Now, unfortunately, we couldn't go back in time with our instrument because it had actually been commissioned until like the 2015 or 2016 or so. So we could go back in time. So the next best thing we do was look around to see who else observed the system, and that's where the Hubble Space Telescope comes right in. And the image actually right behind you was the archival detection of this point's AB Auriga B with the now decommissioned and dead, basically, NICMOS camera.
And that's it, the sort of white blob down at the bottom of where the star is.
Exactly.
Yeah. But on this image, the star is blotted out by a coronagraph.
Yes.
Does Hubble have a coronagraph?
Yeah. So NICMOS, when it was operational, did have a chronograph mask, and so like you see that dark circle is very large. It just happens to be small enough that it doesn't block the detection of this protoplanet. Right. The current instrument on the Hubble Space Telescope, STIS, which is operating at visible wavelengths, that also has a suite of like bars or other masks that operate as a chronograph. So Hubble does have chronographic capability.
Okay, all right. But I mean, it's funny though, because like you are pushing the technology to the utter limits, both in terms of what Hubble can do and what Subaru can do from down here on Earth. But there are a suite of instruments that are in the works, either recently launched or under construction now, that are going to change. They're going to change everything for what you're doing. And there's also, but I want to, and we'll talk about sort of the future of just this whole science in a second. But this idea of protoplanetary systems looking like tiny little solar systems, we've seen this quite a bit through radio observations and microwave observations. So was this a surprise that protoplanets looked more like tiny galaxies than records?
Well, I think you expect from a disk that's gravitationally stable, but only a subset of them show those features. I mean, there's a great diversity in the appearance of protoplanetary disks from in the radio or in the submillimeter, like from the ALMA or other facilities, right? So there are probably a lot of different mechanisms going on in these systems that may be dominant in one and but not dominant in the other. The other system with confirmed protoplanets, PDS-70, is a little bit different. So it doesn't have like 7 or 8 spiral arms like AB Auriga has, but it has this cleared cavity, and then there are these 2 protoplanets that are sitting in the middle of this cleared cavity, right? So there's a great diversity in the appearance of protoplanetary disks and the sort of the general morphology or structure of planetary systems in the process of forming.
I mean, there was like a list of images that came out from the ALMA telescope within the last year or so, and it was about, I feel like it was about 20 or 30 of these planetary systems that show these incredible features. Like I said, some have concentric rings, some have almost spiral arms going on, and so I guess that's what I was wondering. It was just like that. The concentric rings make sense because you've got planets that are forming in these rings, but to see these more interesting structures, it makes you wonder: are there inflows of gas? Is there a much faster migration of the planets than were originally expected, especially early on? So, do you think we're kind of at that point now to get a sense of how planetary systems work early on?
Well, I think we're at the point where it's clear there's that there are diverse images of these protoplanetary disks that identify a lot of different dominant processes going on for sure. And I think what's really exciting is that once you have discoveries like the PDS-70 protoplanets or this one, that really spurs or justifies a lot of dedicated follow-up work. That maybe if we look a little bit more closely at some of these other protoplanetary disks that do show some of the features that you described, we may find examples of the two kinds of protoplanets that we've identified thus far, or maybe even something entirely different from or at least a little bit different from PDS-70 or AB Riga itself. I mean, those are really open questions, I think. But I think just having these two discoveries really breaks open the dam to really focusing on this kind of on this area of science further.
The PDS-70 image, and I apologize because I'm gonna have to sort of like explain it, and it's like dancing about architecture. Is I use that as the opening slide for a talk that I gave a couple of years ago as like one of the most important images that I had ever seen in 20 plus years of astronomy journalism, because it is an actual photograph of an actual planet that is actually forming around another star. That it is, all of the planets, the 5,000 planets that are in the exoplanet surveys that we know of so far, they are using the radial velocity method, using the transit method, using the microlensing method, and a couple others as well, pulsars, things like that. But we're now taking pictures of planets directly. And now all of these problems where your planet has to be perfectly lined up with the star, that all goes away. So where we stand right now with the current instruments that you have at your disposal, what are the limitations of what is possible in direct imaging of exoplanets?
Sure. I guess first to start, I agree with you that the direct imaging itself is exciting. I mean, I put sort of smugly, I like planets I can see.
Yeah.
Right.
Yeah.
I'm really biased on that, but I like planets I can see, not those that I can sort of like infer through a series of arguments based on physics. But seeing is believing. But where are we right now? I think we're still at the point where we can only detect planets that are self-luminous and they're young. So even the best systems on ground-based telescopes right now can get contrast in the order of like 10 to the minus 7. So that's what, like a 10 million to 1. That's good enough to detect on a if we know exactly where to look. That's good enough to detect maybe a young Jupiter analog.
Now, when you say self-luminous, you mean like it's giving off enough heat that it's perceptible in the infrared spectrum, and you're not trying to rely just on the reflected light of it.
Correct. Yeah. So we're not seeing light reflected from the star. We're actually seeing internal heat from the planet. So the planet is collapsing, shrinking in radius. So it's releasing that gravitational potential energy, and it's shining. So that's what we're seeing when we're seeing all these images of like planets like H8799 or any other sort of emblematic planet. That's what we're seeing. So we're kind of stuck at that point until we can get to contrast another factor 10 or factor 20 better. So below 10 to the minus, about 10 to the minus 8 or so below. Now that would be good enough to start to detect planets in reflected light. And so then we don't really care quite so much when whether or not the system is young, and so the planets have to be self-luminous, and so they would shine enough for us to be able to see them. But we can just we can look at systems that have ages comparable to the sun, for example. So that's a very different kind of expansive phase space that we cannot really access right now. But I think even right now, it's still very, very exciting what we're able to do.
And so, like, what is the state of the art? What would you say is like the most powerful direct imaging tool at our disposal today?
Okay, so I think the most, and keep in mind, I'm going to be a little bit biased in this. I think the most Skexio is I would say is the most advanced. Then the one that has demonstrated the best performance right now is Sphere on the VLT.
Right.
It relies on technology that's a little bit older, but it is so well honed. It is so well optimized. And that's what you can do when you have an army of people who are very talented, work very hard, who throw all their effort at one instrument. So I think those two instruments right now, one in the north and one in the south, are kind of at the leading edge of what we can do with high contrast imaging.
And so really we're limited to young stars, hot planets, ideally a fairly big separation between the star and the planet, and a fairly, by a factor of, what did you say, a few million in terms of the brightness of the star compared to the brightness of the planet that the coronagraph can actually block out. That's the state today. So what's coming? What telescopes or instruments are around the corner? They're going to give us the ability to push this envelope.
Sure, I think you'll see two. Okay, I think there's really three major advances. So one is that first, right on the front burner, the James Webb Space Telescope will have some truly transformative high contrast imaging properties. It's only 6.5 meter telescope. It's optimized at longer wavelengths, and so it's not going to be able to look as, I think, not going to be able to do quite as well looking very close to the star, and as Sphere or maybe Skexio, in my opinion. Those instruments will still win perhaps by a substantial margin, but it will be exceptional at getting direct images of planets around the nearest stars that are maybe a little bit old and that are still shining. The planets are still shining in the mid-infrared wavelength, so maybe at 5 microns or 10 microns, which that's really tough to do from the ground, right? Because the atmosphere exists, and it's contributing a lot of background emission.
So what's your definition of old, though?
Sure.
Like a couple of million years old as opposed to a million years old?
No, I think my definition of old here would be things on the orders of hundreds of millions of years old. That's when the thermal infrared or the mid-infrared really start to completely overpower the near infrared in terms of our detection capabilities, right? And even for things a giga-year old, I mean, James Webb would be able to potentially detect planets around those stars
because they'll still have some latent heat.
Yeah, and that's going to be really tough from the ground, unless you can detect planets in reflected light.
That's exciting, but I think, what everybody wants to hear is Earth-sized worlds orbiting around sun-like stars, or even like an Earth-sized world around a G-type star would be fine. Maybe even an Earth-sized world around a M dwarf would be okay, but a billion-year-old Jupiter analog around a young star that's only a billion years old at the maximum. I mean, it's going to be exciting for you guys. But for us to find out, to answer this question, are there other Earths out there? It's not going to be able to.
Yeah. So that goes into the other two parts of my answer.
Yeah.
So on the ground, what you will see in the next 5 years or so are upgrades to the leading extremeo systems. So upgrades to Sphere, upgrades to Skexio, upgrades to GPI. And those will start to push down to 10 to the minus 7 levels of contrast, and maybe if we're really lucky, we can get a little bit better. The important thing with those instruments is that it's not so much their power in and of themselves, but the fact that they serve as prototypes for the kinds of dedicated planet imaging systems we want on 30-meter class telescopes. That will get really interesting because with having a much larger telescope, you get far sharper images. So you can look really close to a star compared to what you can do now, even with Keck or VLT or with Subaru. So close that in fact you can access the habitable zone around some of the nearest low mass stars. All right. So the habitable zone, like roughly what we think is kind of equivalent to where the Earth would be around an M star. A contrast for an Earth-sized planet is about 10 to the minus 8 or so, right, roughly. That's still challenging, but it's not infeasible from the ground in the near future.
So just to clarify, then you've got to have some kind of light blocking system that is able to factor out 10 to the minus 8. What is that? 100 million? Is that right? 100 million times, or the planet will be 1/100 millionth the brightness of the star, and you've got to be able to block out that star, but still get the light of the planet and be within the habitable zone. That's tricky.
It is challenging, but I think the thing that's exciting is that the leading instruments right now are proving technologies that we will need for those capabilities. They give us confidence that we may be able to get to that goal. It just really depends on the amount of funding, the amount of some breakthroughs in new waveform control and coronagraphy technologies. I think we can get there within the next 15 years. I think that's definitely feasible.
And those are existing telescopes. That's the Very Large Telescope. That's the Subaru. That's Keck.
Exactly.
Right. Okay. 8-meter class telescopes.
Exactly. So if you look at the design, for example, of Skexio, it is very similar to the design of most of what is the planetary systems imager, which is a proposed instrument on 30-meter telescope. And similarly, like Sphere is prototyping a lot of the technologies we need for an Earth imaging system around the European Extremely Large Telescope. So we're not going to have this really big telescope and a promise of trying to do this amazingly transformative science and have to start from square one.
Right.
So we're using the technologies on the current telescopes to get us ready for prime time, to get us ready for being able to do that kind of transformative science with a next generation of telescopes.
So say we bolt that upgraded version of Sphere, or how do you pronounce it?
Skexio.
Yes. Skexio. So we take a Skexio or a Sphere, and we bolt that on to, say, the European Extremely Large Telescope, 39-meter telescope. Where does that get us?
I think that gets us fairly close to where we need to be. There's still some challenges we need to work out, and this goes into the weeds of different error budgets with the wavefront error, specifically in terms of chromatic wavefront error. In terms of servo lag, which basically means, by the time you apply some correction to your DM to correct for turbulence in the atmosphere's already started to change, right? So there's still issues we need to work out, but if we can essentially get these systems like Sphere or Skexio working on a much larger telescope, we're in a very, very, very good shape, I think.
And when you say good shape, so like, so if the factor is 100 million to get from an M dwarf to a planet in the habitable zone around the M dwarf, what is the factor that we need to get to for a sun-like star with a Earth-sized planet in the habitable zone?
So that's true. That's far trickier from the ground. So the contrast we would need to be able to detect a true Earth analog around a sun-like star is 10 to the minus 10. So.
Right.
So that's another factor of 100.
Right. 100 billion.
And I think I've had some discussions with many people about whether this is even possible from the ground. I take the optimistic position, which I think Olivia Guillaume agrees with me a little bit. Is that if we had the budget of the U.S. military, we could do this from the ground. to the minus 7. Sure, why not?
Yeah.
We can do
One less aircraft carrier, one more mega telescope.
For the price of the entire fleet of F-22s, we can do a lot, right? But I think feasibly, to get a reflected light detection of a true Earth trend around a sun-like star within the expected budget and the expected human power thrown at the problem from the that's probably something that's going to take space to require us to do.
Okay.
But we can get perhaps a thermal emission detection of an Earth around a sun-like star from the ground, like at about 10 microns or so. And so the contrast for an Earth around a sun at 10 microns is only 10⁻⁷
right. But now we're back to a young Earth that has got internal heat, like a magma hellscape going around a young star.
No. This would be for a true Earth.
Oh, okay.
Yeah, and then that's because just from Planck radiation, the black body of something 250, 300 Kelvin peaks pretty close to about 10 microns, and so we're kind of being helped by that. Also, there's the signature of ozone as a broad feature at 10 microns that could be a potential biomarker. So that might be possible around about a dozen stars or so.
So there's essentially about a dozen stars close enough to us that, but again, we don't have to worry about them being lined up. Now we can just take the pictures directly.
Exactly.
Yeah. So then let's go to space. What does the space version of this look like?
So space is also extremely exciting. So the mission that I'm most excited about right now is the Roman Space Telescope. Essentially our former or borrowed spy satellite telescope, and this telescope has as a component the chronographic instrument, which is being treated as a technology demonstrator, not so much as a science instrument. So what they're going to try to do is demonstrate for the first time ever active wavefront control in space to be able to get to contrast below 10⁻⁷. So below what we can feasibly do from the ground with a Keck or a VLT or a Subaru in anytime in the near future. Right.
It's interesting to me. I mean, the Nancy Grace Roman telescope, it's the same size as Hubble, has a much wider field of view, but then it's being given all of these much more kind of aggressive goals to characterize dark energy, to find potentially hundreds of thousands of exoplanets through microlensing, and so on and so forth. Is it the instruments? What makes it special to be able to do this kind of work, and especially what you're talking about?
Sure. Well, I can speak about the high contrast imaging capabilities for Roman. So what Roman will be equipped with is essentially an AO system in space. And then it'll do something called focal plane wavefront control. So instead of an atmosphere that's blurring starlight, you figure out how the starlight is being blurred and you use the mirror to correct for that. No, you're actually looking at the science plane itself to figure out where the sort of residual glare of the star is, and then modulating two deformable mirrors to be able to remove that at the science plane.
Wow.
Right? Yeah, it's crazy. And because there's no atmosphere, you have a different source of aberrations. These operate slowly, so it's a kind of a different regime than on the ground. But they're still able, in principle, if we believe the laboratory tests thus far from JPL, we should be able to get to 10⁻⁹ contrast in space with the Roman Space Telescope at subarc second separations, which is a factor of 10 to the 4 better than what we could do with the Hubble Space Telescope. But I guess essentially we have these additional mirrors in an advanced chronograph.
Yeah, but I guess I'm a little confused. So, like, with adaptive optics here on Earth, you are deforming your mirror with pistons to essentially the atmospheric perturbations that you're detecting with a guide star. But you're out in space, and so there's no atmosphere. So what are you modifying your mirror against?
Mm-hmm. Sure. So there's still there are two things. So there's still additional optical aberrations due to any optical system. No optical system is perfect, right? And the other thing is that if you if you just have just an unocculted image of the star, and say the optics are perfect, it will look like the Fourier transform or the pupil function. It will just like for a circular aperture, it will look like an airy disk, right? So you can use the deformable mirror to dig a dark hole, to essentially to reform the way in which light is distributed, to be able to see much deeper than you could without the manipulation of those mirrors.
Right. I mean, I know that, say, with coronagraphs, like part of the magic of the coronagraphs is taking the light from the star and then interfering with itself to know what to remove. But it's a fairly fuzzy, kind of messy process with a lot of light that bleeds out through your attempted interference. So, I mean, is that part of it, or I'm completely off base here?
No, the chronograph does do a lot of heavy lifting as well. And so with the chronograph, so the different chronograph masks that are being deployed for Roman. And so one of them is the hybrid LEO chronograph, which is basically a really souped up version of the LEO chronograph that we know and love, that will get much deeper contrast than that, the older design that's been around, for decades. Another one is this crazy thing of the shaped pupil chronograph, which has this sort of like strange pattern which throws light out of a region in which you want to be able to look for planets. And so the advanced chronograph technology is a key component of the Roman Space Telescope's high contrast imaging capability, and thus something that's really crucial to be working well if we want to be able to image planets in reflected light, which we think we can do with Roman Space Telescope.
So this is all great, but 12 stars, maybe from the ground, Roman's going to get a pretty wide view, going to have a really tricky time. So now we're going to have to move beyond what's planned, what's in engineering right now. What's it going to take to look in all directions, to observe the stars and go, no planets there, no planets there. Oh, we got an Earth-sized planet over there in the habitable zone. That's interesting. Super James Webb follow up on that one. Keep going. What's it going to take to give us a better survey of what's really out there directly?
Sure. So we need both the ground and space to be able to do this, and we also need other techniques for planet detection to be able to do this. So from the ground, again, the 30-meter class telescopes will get us. If they work as we think they will get us the contrast we need to be able to image planets in reflected light around M stars, which are the most abundant types of stars in the galaxy. And so, I think I did some calculations for a paper a few years ago. On the order of about 20 or so M dwarfs would have a detectable Earth around them in the habitable zone if such planets existed, and we targeted them. Now, for sun-like stars, we do need a dedicated flagship mission for imaging an Earth. And so that would be the successor to the Roman Space Telescope, the kind of mission that was recommended as a top priority from the 2020 decadal survey, the sort of LUVEX or whatever you want to call it, like a very large,
Is that the new acronym then? Half LUVOIR, half HABEX? All telescope?
It's sort of in between LUVOIR and HABEX in terms of aperture, so I'm going to call it LUVEX.
That's good.
I think that might actually be the sort of colloquial name for it at this point. But the basic point is that NASA is prioritizing exactly what you described, a dedicated Earth imaging mission to be able to identify a true Earth twin around a sun-like star in reflected light and get evidence for habitability, or at least to be able to test for that hypothesis.
So this would be like a James Webb-ish sized telescope, but with Roman-style detectors and maybe a starshade too?
I think this fairly close. And so it'd be the nominal aperture is roughly the size of the James Webb Space Telescope, but the key sort of our arsenal of instrumentation would lean heavily into the types of things we are trying to prove for the first time with Roman Space Telescope. So active waveform control in space, very aggressive chronograph masks to be able to get extremely deep contrast. Those two things will be critical, and that's kind of what we have in mind for a direct imaging flagship mission.
And how much of a sphere do you think that that kind of a flagship mission, Lubex, would be able to detect?
I mean, in terms of like out to what distance?
Yeah, yeah. I'm just sort of
Sure.
imagining, you talk about 12, 20. How far do you think you'd be able to go?
Sure. I think I would have to go back to what the yield estimates are for Habex and Louvoir, which are kind of set of are a little bit of our boundary conditions for what's possible, but on the order of tens of Earth-like planets, given our estimates for the frequency of rocky planets in the habitable zone. And also just to emphasize this point, having sort of precursor information of these systems with the indirect methods, with radial velocity especially, possibly with astrometry, that will be very helpful, right? Because you could have a direct imaging system that could image a planet 1 trillion times fainter than the star, but if the planet just happens to be behind the star at the moment you target it,
Right.
it doesn't matter, right? So having this sort of ancillary information in hand, this information in hand before you try to target the star will be very, very helpful.
But but then you're sort of then going back to relying on the planets that you've discovered using the radial velocity method, or using the transit method, which is say 1% of the star systems that are out there happen to be lined up to the point. And it totally discounts the planets that are really far away from the star. The chances of them lining up are remote. And the timelines to be able to see them orbiting around their star, again, stretch off into the decades. If you're going to try and find another Jupiter, you got to wait 30 years to get 3 observations. So what would it take to be able to do a survey?
Sure. So I'll try to answer both those questions in turn. So yeah, the probability of a chance alignment of an Earth around a star detectable by the transit method is pretty low, especially for a sun-like star. But again, the radial velocity method is still advancing. We're trying to do better and better, beating down the systematic noise from a host star. There are rocky planets we've detected through the radial velocity method that are that start to get pretty close to what we want to be able to directly image. And so that, I think, after another decade or so of advancement with RV, we will start to have a fair number of good candidates to be able to focus on with our direct imaging instruments. The other thing too, for Jupiter-like planets, those might be even more possible with for direct imaging once we have precursor data with astrometry.
Right.
Okay. Yes. So right now there's this there's a mission that's up in space taking data called Gaia with the European Space Agency, which has exceptional precision from microarcs, on the orders like a few or maybe a 10 microarcsecond precision in astrometry. That's good enough to detect the signature of a Jupiter-like planet at a few AU or so on nearby stars. And so if we have if we have precursor data from radial velocity and from astrometry, we should be able to identify enough systems to be able to directly image an Earth or Jupiter or things in between.
So Gaia, I mean, we're still waiting on that next big data release from Gaia, the one with all the planets. But in theory, there are tens of thousands of extrasolar planet candidates in that Gaia data that haven't been teased out. And I guess you've got these stars that are pulling little circles around in the sky because the planet is yanking them around. But we're seeing it at a completely different angle, one that we couldn't detect with any of the other systems. So do you feel like you could take that Gaia data and the closer the stars are, the louder the signal is going to be, and then that will be your list to go through of exciting candidates?
Oh, I think certainly for Jovian mass planets, I think we're already there. So, for example, if you look at some of the planets that have been directly imaged, HR8799e, Beta Pic B, those have those induce detectable astrometric accelerations on their host star, identifiable from Gaia. So we're already there with
Hmm.
those. And so it's really just a matter of time before we identify a planet through both astrometry and direct imaging. That's only a matter of time, and you will not have to wait very long for that. So I think that's right around the corner. For sure.
And so what do you think, we sort of imagine this, we're on this journey of planetary exploration, and back many planets that are actually lined up, as I mentioned earlier. So what really will what is the future of planet hunting and planet observing over the next few decades, do you think?
Well, I think that there are a couple innovations that we're starting to see. One is combining techniques, and so you can have a long-term radial velocity, for example, long-term radial velocity drift, right? But you don't know quite what that is. But if you combine it with astrometry, which is is a different technique, but also is sensitive to a dynamical influence of the companion, that can be very, very helpful. So you'll see the combinations of techniques which will start to carry the weight. I'm actually, to be honest though, I'm actually more excited right now about the ability to identify things that spur substantial follow-up characterization. So not just simply bean counting, not just saying, well,
Right.
we have 5,000 planets, now we have 10,000, 20,000, 40,000, 100,000, but to actually understand these as, full-fledged astrophysical objects, right? So understanding not just simply, that they're there and that they orbit their stars, but what the orbit is like. Are there other planets in this system? Do they show evidence for orbital resonance? Are they eccentric? What are their atmospheres? Do they show evidence for oxygen or, sorry, no, like carbon monoxide or methane? What are their gravities? Do they show evidence for clouds? So like the first directly imaged planetary system, HR 8799 has spurred so many follow-up papers focused on trying to understand its atmosphere. So imagine doing that for 25 directly imaged planets, and then 50, and
Yeah.
100. We'll be dealing with a flood of data, and I think we will start to see the numbers of directly imaged planets pick up in the next 5 years, and many more detailed studies.
I mean,
So I'm really most interested in that. I think.
yeah, I mean, I'm right now. I'm definitely at the point now where if someone announces the discovery of new planets, I'm like, that's not really news, and we don't run it on Universe Today unless something really interesting has happened or there's a really cool picture to go along with it. So let's say that we did find a really interesting planet, and we wanted to understand that one planet really well. And instead of building various survey telescopes to try and find lots of them, we wanted to just the equivalent of sending a rover to this planet. What is the telescopic version of that could get us as much detail as humanly possible in some really interesting, some world where we're seeing some kind of interesting biosignature, sea, land formations, mountains? What could we do?
Well, I think it really depends on the type of the planet that you're focusing on. So I'll start with
It's another Earth.
Okay, another Earth. Okay,
Yeah,
sure.
yeah.
So I think we want a couple of things. First of all, we want some dynamical mass estimate. We want some constraints on the orbit due to the planet's influence on the star. So this really calls out for indirect techniques that are sensitive to that. So either RV or astrometry. And so a dedicated RV or astrometric campaign can be able to tease out this information in detail. We want to be able to also understand, the atmospheric properties of this planet. So we need not just simply a detection in some broadband paths, but we need a spectrum. So integral field spectrograph would be ideal. If we really had a large telescope and we're willing to throw a lot of time at this, which it sounds like that's what you're having.
Yeah. One telescope. Its only job. It only has one target.
Its only job is to observe this. Okay, yes.
This one planet. Yeah.
So we would want an IFS with a low resolution mode and also a very high resolution mode. So be able to resolve different spectral lines themselves. Now, we've done this already with the first directly imaged planets, and so there was this really amazing paper by some of my collaborators / competitors on HR8799C that resolved outlines for carbon monoxide and methane, and then try to connect that to the formation process of that planet. So that's something, that kind of thing is what I would like to do. Would like to do with an Earth-like planet, really high spectral resolution. Someday in the future where that would be possible, to be able to get even more detailed information about its atmospheric properties. And then also just to kind of put the system in context. So if we had aliens looking at the Earth, aliens looking at the solar system, and their telescope was infinitely powerful, they wouldn't just simply see the planets, they would see the Kuiper belt, they would see the asteroid, potentially the asteroid belt, and try to understand the way in which the leftovers of planet formation and the planets themselves interact. And so that'd be another component I'd be interested in. And that might require a telescope that is capable of doing high contrast imaging at different wavelengths than we would normally try to focus on for imaging the planet itself.
Would it be a space telescope, do you think?
I think it'd have to be a space telescope, I think, at this point, to really do all of that.
Yeah.
But just to be very, very clear, the ground will be able to do a substantial amount of transformative science, and I feel like it's a fairly reasonable possibility that the ground would get the first direct image of an exo-Earth around one of the nearest low mass stars. I think that's a fairly plausible scenario in the future.
So I have a weird question that goes back to the sort of this original star, the original planet observation that you made. This double Neptune distance for the existence of the planet, that sounds remarkably similar to a hypothesized planet 9 here in the solar system. At that same kind of distance. Is it possible that we could, if we did have a planet 9 that is, rumored to be a Uranus, Neptune mass planet orbiting out double, triple the distance of Pluto, could it be possible that it followed that same formation method at that distance as opposed to the more standard method?
I think probably the best people to ask the question to would be some theorists. My initial reaction is that would be difficult because the disk instability mechanism does really good at making massive planets. It starts to struggle a bit to be able to form planets that are lower and lower and lower mass. It almost has like the opposite problem a bit than core accretion.
All right, it was a shot. Maybe we got a theory for Planet 9, but maybe not. Yeah. Well, Thayne, absolutely fascinating. If people want to follow your work, what is the best way to keep track of what you're doing?
Sure. So I do have a Twitter account that I tweet on science results all the time. It's AstroThayne, so AstroThayne, and so just that's my handle. You can follow me there. I think there are other good sources for following exoplanet news. So there are astronomy Facebook groups. If you're a professional astronomer, there's also the Exoplanet Direct Imaging group. So there are a lot of outlets to kind of keep up to date. And the other thing I do, I read the archive almost every day, like just like the newspaper. And I always look through very interesting papers in my field and even in adjacent fields. So that's I would encourage readers to do that.
Yeah,
but
yeah.
Also,
they're surprisingly readable. I find, like, even though my background is in computer science, you can read you can read the introduction, you can your eyes can haze over the middle part, and then you can read the conclusion and understand what they're proposing or what has been discovered quite readily.
Yeah. And also, I mean, if you have a question, if there's something related to this paper or one that is similar or sort of the general topic of direct imaging, you can just send me an email and I'll be happy to respond.
Wonderful. Well, thank you so much for answering my questions and letting me kind of express my enthusiasm for direct imaging. I'm super excited about where this field goes because I feel like this is the one that gets us to that other Earth, and obviously that's sort of the holy grail for a lot of the people who are really excited about exoplanets. So thank you so much for continuing on this science, and hopefully you'll get that telescope, that next generation telescope that's going to do what you need. Yeah, exactly. Awesome. All right. Well, thank you so much, and good luck with your work.
Thank you.
All right. Take care. find the button.